Sounds great. Well, thanks, Lynn, for helping put this together, and thanks everyone for coming. So this is going to be an introduction to PyTorch, which is one of the most popular libraries for training neural networks. We're going to just go over a little bit about neural networks, a little bit about PyTorch, and then about convolutions, which is a great tool for using spatial data, for working with spatial data. We'll talk a little bit about spatial data. We won't maybe go into too much depth in examples. Sort of the downside of neural networks is that, especially to do something interesting, like with a spatial data set, they take a while to train. So I won't have you sit here for 6 hours. Um, but so we'll get through it. So this is all done in Python. I guess I'm going to assume some basic familiarity with Python. If you're maybe more of a MATLAB person, you'll see that a lot of it is pretty familiar. And then lastly, so I'm pulling this off of a notebook I wrote. It's available at my GitHub at this link right here. If you want to follow along, this basically has all the code that I'm going to be showing here, as well as some explanation that I'll be talking about. But it's kind of there for you to work through if you want to, but it will be pretty repetitive to what I'm doing. All right, so let's get into it. So we'll start with a really, really simple neural network, training it without PyTorch to a certain extent, and then seeing what it is, talking a little bit about it. So to start out, we'll generate some data. So it's using NumPy, generate some random kind of linear data with a bit of noise. So we'll visualize that. And, so really simple relationship, should be very easy for any sort of method to learn this relationship. And typically we'd use like a linear regression to maybe model this data. We collected it in the field or something like that, we'd see pretty clearly that it's very linear. So we can use a linear regression. I'll be using just a built-in regression tool from SciPy. So do a linear regression, pull out that slope and intercept, and then look at our modeled data, or really just that line. So we've done a regression, we've fitted that line, and now we can look at it sort of plotted against the data. So this is about what you would expect. But we'll do the same thing with a neural network, because it turns out a linear regression is really just a simple one layer, one neuron neural network. But so we'll do it the sort of the PyTorch style. So if you're familiar with Python, you've probably seen classes before. So this is defining a class to make objects that are this neural network with this specific neural network architecture. It's inheriting from some sort of larger PyTorch class. We've got our initialization to create the new neural network, which basically says we're going to initialize that larger class. And then we're going to have one linear layer that's sort of from dimension 1 to dimension 1. And then there's this forward method, which is sort of the method that's called when you apply that neural network. We're just going to apply that linear layer. So we'll instantiate it. And then to train it, we need a criterion for loss, and then an optimizer to change the weights of this neural network. So I'm going to use mean squared error loss and this SGD optimizer from PyTorch. That's going to optimize the parameters of this neural net. So that's net at object. I've chosen my learning rate and momentum. Don't worry too much about these. These sort of control how quickly or slowly the weights of this network will change. So we define those. And then lastly, up here I have our data in NumPy arrays. But to work with PyTorch, we need to put our data in tensors. These are really, really similar to NumPy arrays. They behave almost identically, but they have a lot of extra things that come with them. So things that make it easy to load these onto GPUs and use sort of all the fun GPU parallelization that have made neural networks so possible. And then also other stuff for the back propagation to tune those weights, which I'll talk a little bit about later. But so we need to make it into a tensor. Again, it's just our same data set. And finally, we need to train this neural network. So here's our training loop, which I'll go through. So we're going to train it over 10 epochs, which basically means the neural network is going to see each data point 10 times. We're going to keep track just over time of the loss of the neural network, so how much error there is, and then the weights and biases, which are really just parameters of that one linear layer. And so basically for each epoch in this data set, so just 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we're going to pull out each data point. I've called it input and label. This is really just X and Y. Label, this is just more of like the parlance of neural networks. So you'll see this a lot if you're maybe looking at other people's examples in code. But often we call the thing that we're trying to like predict or infer a label, just because so much of the initial neural network stuff is done kind of for classification. We're pulling out this input and this label with this input.view. It's basically just a way to reshape this into a set of dimensions that the neural network expects. We'll talk a little bit about that later also. If I were just to put in the regular input without this, it would get a little confused about the right sizing. And then also there's some things you need to do to sort of make the correct type of copies of things when working with tensors because of gradient descent stuff, which again, I'll get into later. So don't worry about that for now. We're going to zero out the gradients of this optimizer. So that's that thing that is changing the weights. So we want to set it to 0 so we can look at the new gradients once we run something new our neural network. Then we're going to run this given input through our neural network. Then we'll look at the loss. So in this case, the mean squared error between what the neural network outputted and what the true point of data was. Then we're just going to save all these for visualization later. And then we're going to back propagate the loss. This is more important when you have much larger neural networks, but the way that we train these things is through what's called gradient descent, where basically look at the derivative of the whole, all the weights in the network with respect to this loss, and then adjust them based on that derivative to be slightly more optimal. That's sort of the thing that makes have made neural networks so powerful, is that we figured out a way to basically take the derivative of the whole network, even if it's contained of a lot of different layers at once, which I'll talk a little bit more about later. In this case, since we have one linear layer, there's not really, don't really need anything fancy to do that, but later it becomes more important to have all this kind of extra mechanisms here. And then we're going to step the optimizer, which really just means we're going to tweak those weights and those biases with respect to that gradient that was calculated so they'll be more efficient. So we'll run that, train it very quickly. So we've trained this neural network, that's one linear layer. But what is it really? And so we can look at the parameters that are stored for this linear layer. You can see like it's got some flags, like it's in training mode. It's got one input feature, one output feature. There's not a lot else that's been set. There's lots of sort of fancier things like hooks that you can do that often come in handy when you're interpreting a neural network, things like that. But then you have these two parameters, the weight and the bias. And so these are parameters that go along with linear layers. Basically, the weight, if this is a linear layer, it's approximating the function y equals mx plus b, and the weight is that m, and that bias is that b. So similarly to that slope and intercept of the linear regression, this is just the weight and the bias for this specific linear layer. You'll also see there's the requires grad equals true flag. You'll see this a lot for different tensors. Basically, that means is that PyTorch should be keeping track of the gradients of these features. So great for gradient descent. So you can look at sort of how things changed in this neural network over training. So since we recorded the loss and the weight biases, and plot these. We can see sort of some change in the loss over time, and then it sort of finds itself into a fairly low value. It tweaks itself back and forth, back and forth. It isn't really improving much. We probably could have cut it off over here and performed just as well. And similarly, we look at those weight and bias values, quickly it finds a weight pretty close to 1, which makes sense for slope. And then, it oscillates around there a little bit as it pops around, looking for potentially a better solution. SPIAS is a little more interesting. You can see that it's been more slowly approaching 0, which makes sense because that's our intercept of our line. So maybe it was good that we let it train for so long, but you can see that it wasn't really impacting the loss that much. So this neural network was really just a linear function that we've trained, and we can compare it to our linear regression. We'll pull out that weight, pull out that bias, and we can compare it to our linear regression. Typoed something. So here we can see in that dashed green line, that was our linear regression, and then here's our trained neural network. So really, really similar, a little bit different. You wouldn't want to use a neural network to do linear regression, but you can. Because at its heart, a neural network is usually just a bunch of linear regressions chained together. So I have this figure that I pulled from Prince 2023. It's a recent book on deep learning that I really, really highly recommend. It's got great figures. It's really well explained. It's available online for free as well. So you can see that we have something close to, we have these joints, but 3 linear regressions in this figure. These would maybe be 3 different layers in our neural network that then are all added together to create this function. And so you need these little hinges because if you just had 3 lines, if you add them together, you get another line. So you wouldn't be approximating anything more complex or nonlinear. So these hinges are what's called activation functions, which are used to add nonlinearities into your neural network. This right here is what's called the ReLU activation function. It's really commonly used. What it does is it basically says it takes your output and says if it's below 0, I'm just going to set it to 0. So here, below 0, so it's been set to 0, etc. And so that's how you get these hinges that you can add. Here, it's also just been flipped by this extra weight right here, so you can have it's not always get some negative numbers in there, things like that. So at its heart, that's what a classic neural network is, which is a bunch of these linear layers, these linear functions chained together. So here we just have one, but you could imagine we do it again and again and again and add them all up or feed them into each other and things like that. So that's sort of at the heart of a classic neural network, and you've seen a little bit of PyTorch. And so before we get into convolutions, does anyone just have any questions, anything that wasn't clear? If not, we'll move on. So convolutions. This is why we're all here. So convolutions are basically something you can use instead of just that linear function, and they're really great for spatial data. They were developed for image recognition. They are used for all sorts of things. And basically what it does is it lets you look at regions together instead of looking at maybe each pixel of your input individually. So what you do with a convolution is you have, instead of just one weight or a set of weights that you're applying to your input, you have a window of weights, and you slide this over your input. So here in this case, we have these 9 weights that are overlapping these 9 pixels. And then you just sort of do a weighted sum. So 50 times 0.1 plus 50 times negative 0.2 plus 90 times negative 0.1 plus 80 times negative 0.2, et cetera, et cetera. And then you add this all up, and that becomes sort of one pixel or feature or activation in your output. So here, this set of 9 becomes this sort of pixel in the output. You could imagine that if we were slid over one so that we are overlapping this 50, 80, 60 and not this 90, 90, 90, that would then correspond to this pixel in the output. So again, this is going to end up being the same basic architecture, where instead of a linear layer that you're applying to your input of maybe just one point, it's this thing that we're sweeping across our whole input and then passing on to our neural network. So we can see an example of what this convolution looks like. Just going to load in some sample spatial data. So here, this is just a modeled landscape. It's not real string power, diffusion, numerical model solved over like a million years, but giving some very dissected valleys, nice ridge, things like that. So to make this work with PyTorch, we need to make it a tensor. We also need to add an extra dimension. That's what this sort of unsqueeze command is doing. If we look at the shape of this, you can see instead of just being a 300 by 100 image, there's also this one. That's because PyTorch expects to work with like multi-channel images typically, and it just wants to know that this is just a one-channel image. So it's one channel with 300 rows and 100 columns. But so if you're used to maybe working with just one channel data sets, one dimension data sets, you'll need to unsqueeze them frequently. So we have our test input tensor, and we'll just create a convolutional layer and we'll manually set its weights. So here I'm creating a 2D convolution that has a one channel input and a one channel output, and then it's got a set of weights that's 3 by 3. And then this time we're just going to manually set our weights. Typically it'll instantiate them with random weights because it assumes you want to train them. But here I've set these weights explicitly, -1, 1, -1, etc. And now we're going to apply this convolution to this input data set. And then we can take a look at its output. So it's definitely done something. It's pretty funky, very interesting. You can see it's inverted the topography to a certain extent. These high ridges are now low. The valleys are now higher. It's also added in some interesting noise to some extent. So that isn't necessarily meaningful, but just kind of shows you what the outputs of some convolutions can look like. So typically in a convolutional neural network, we have one or more of these convolutions, and then we're training them over time. So we'll sort of do the same thing we did with that really simple linear data, and we'll train a neural network to see if it can reconstruct this convolution, just given this input and this output. So now I'm going to talk a little bit about data loaders and data sets. These are PyTorch classes that help pass data into the neural network during training. They help like batch data for training on GPUs, things like that. As you can see, when I trained this network here, I didn't actually use a data loader. I just pulled out this data directly, but you'll often find yourself using them, especially when you're doing sort of more heavy work, or if you're following other people's examples, etc. It gives you also some extra stuff besides just the GPUs of helping you like apply transforms to your data that are necessary, things like that. If there's sort of pre-processing you need to do, these can be done in the data sets and the data loaders. So they're handy for more than just the GPU stuff, but that's maybe one thing to think about. So here I've made a really simple data set, which is just going to always send this input and output. So again, a Python class, we inherit from this larger PyTorch data set. When we initialize it, we have a length, which is going to be basically the number of times this sample will be returned, and then the input and the output that will be returned. So we're just setting these as class variables. Then we have to define this length function. This is just because of how data loaders work with data sets. It's expecting sort of a set of data that has a specific finite number of samples. So we set that length. In this case, it's arbitrary because we're just using the same thing as many times as we want. And then we also have this get item function, which basically says for each index that it's given, return an item. In this case, it's really simple because we're just returning the same thing every time. So this index isn't actually used. Later on, I'll show you a more complicated data loader that will actually use this a little bit so that you'll get some more hands-on experience with real usable data loaders, data sets. And so then, each time we get it, we just are returning this input and this output. And you can see I'm also using this clone and this detach, et cetera, et cetera, et cetera. And that's because of the gradients that PyTorch calculates behind the scenes. So basically, when you're making all these tensors and these neural networks and these layers, and you've connected them together, PyTorch is keeping track of that in a graph behind the scenes. So when you fed data into a neural network, it's now sort of connected to it and connected to the weights of the layers via this graph. And it has that graph so it can keep track of gradients when you're doing that gradient descent and that optimization. It needs to be able to calculate like the derivative of the weights with respect to the inputs, derivatives of the inputs with respect to the weights, all sorts of weird things like that. And so what that means, it'll maybe freak out if you pass the same input through it again and it already has gradient set up. It'll get confused. It'll, won't be able to do gradient descent properly. And so it'll fail and let you know that. And so often you'll find yourself when you're working with data, you'll have to end up detaching it and or cloning it. I think we'll see that later when we look at the output of a neural network. We're trying to plot it. We actually need to detach it first before PyTorch will let us turn it into a NumPy array. So you'll find that comes up often, but just know that the reason this is happening is it's part of that gradient descent calculation. So we'll create our data set and our data loader. So again, here we're just creating our data set. We're giving it a length of 2000, which means that it'll return 2000 copies of this input and output. We're saying give it this test input and this output, and then we're passing it into a data loader. So the data loader is sort of what PyTorch uses to pull data from that data set. There's other things you can change about it, but we'll just focus on the batch size. So this is sort of the number of inputs that it passes to the neural network at once. You can think about that in that way. And basically it will process those 64 inputs all together and then optimize the weights. So basically the smaller this batch size, the more often those weights will update. There's lots of research about like optimal batch sizes. Sometimes you want it to see more data before it updates. Sometimes you want to see less data. Most people use between 64 and 256. I wouldn't worry about it too much unless you're really getting in the weeds with the stuff that you're training. 64, in my experience, has worked just fine. So now we'll make a really simple convolutional neural net and see if it can learn this convolution. So here's our convolutional neural net, again, really similar to our one-layer linear neural network. In this case, we just have this convolution. And then the operation this neural network does is it just applies this convolution. So we'll create our neural network, we'll create our loss criterion, we'll create our optimizer, we'll keep track of losses and weights. We'll run this for 5 epochs. So typically an epoch is, how many times does it see the data in its training set? In this case, we only have one piece of data in our training set, but we set up our data set to sort of have it there in 2000 copies. So this will really mean it will see this input data 10,000 times, 2,000 times in each epoch. So then we're going through this data loader, we're pulling out our data, we're getting our inputs and our labels, we're zeroing the gradients of that optimizer, we're calculating the outputs of those inputs, and really it's like 64 at once because that's our batch size. We're looking at our loss, and we're back propagating it, and then optimizing our weights. And here we're just recording our losses and our weights for our own purposes, just for visualization. So again, what's really going to happen is that this network will see 64 copies of this input at once. It will run them through the network. It will look at the loss. It will calculate its gradients, and it'll optimize the weights accordingly. Then it'll do that again and again and again until it's seen each input, which is one of 2,000 copies, 5 times. In this case, batch sizing, seeing more or less inputs before optimizing the weights doesn't really matter because it's all the same input. Oh, goodness. Forgot to run. Been delinquent in running my code. Okay, so this will run. It'll take a little bit, but not too long. Great. So it's 44 seconds. Train that convolution based on that output. And we can look at sort of our losses and weights over time. So a lot of oscillation in the beginning. Same thing with these 9 weights that are trained. Then it sort of seems to find the trend that it wants to be on. And it's found what seems like a pretty low loss. So we can now look at what the output is. We're just going to pass that tame test input into our network, and we're just going to visualize this output once we detach it and then squeeze it to the right dimensions. So it did okay. We can see that it got the general maybe like inverseness of this convolution right, but it's missing a lot of what makes this convolution unique, let's say. We can look at the weights that it's learned, and it's not that similar to what we put in. So it could be that it's just going to struggle to learn this convolution. It could also be that we just need to give it a little more time. So I'm going to run this for, what did I find? Run this for 50 more epochs and then keep training it, and then we'll get back to it. Okay, so above, see how we're doing on time. Great. Before this, I briefly mentioned activation functions, and that was the thing that added the nonlinear, and you use these in CNNs as well. And in fact, in a typical neural network, a convolutional neural network, you sort of have 3 layers together that will make up like what I'll call your convolutional unit. And that'll be your convolutional layer, your kernels of weights, an activation function, and then a pooling layer, which is just used to reduce the resolution of the data to help speed up the network, make it work a little more efficiently, you have to deal with less data. Like convolution, pooling involves sort of sweeping a window across the input, but instead of doing weights, you do something like take the maximum of a window of 4 or 9 or something like that. You can also do the average. There's lots of other pooling metrics, but maximum is the most common. So returning to our convolutional neural network, this were to be maybe more typical, a 1-layer convolutional network. Doesn't really even happen. It would look something like this. So again, we have our neural network class that we're creating. We have this initialization function. We'll create, again, our 1-layer, our 1-channel to 1-channel convolution. We also add this relinearization layer, which is just going to set all output values that are less than 0 to 0. And then this max pooling, which is basically going to go look at 2x2 windows. It's not going to sort of slide. It's just going to go divide it up. That's what that stride is doing. It's saying we're going to go in sections of 2x2, and then look at that, take that maximum. So you could have it slide, and that would reduce the resolution less. You could have it maybe increase that stride and then have it skip whole sections. But this is just a really common, you'll see this a lot in neural network studies. where they'll use a sort of 2x2 max pooling, which is really just resampling that data. Then again, we have our forward, which in this case, we're going to apply that convolution, apply that relinearization, and apply that max pool and return it. So you'll see this series of three a lot in neural networks, but typically they'll sort of be done many times. And so I'll show you some simple but more useful and it's more complex than this, but still relatively simple neural network architectures. This is the kind of stuff you'll see in tutorials, but they still can be quite useful. I'm not going to train them because they take long enough to train. That would be sort of unpleasant in a webinar setting. You can see even our really simple one convolution learning is still going on. But so here is a sort of example of a neural network that is commonly used maybe for a classification task where you want to classify images into one of 10 categories. So again, we have these three convolutional blocks. So we have a convolution, a relinearization, and then a pooling layer. With this, it takes our input, and instead of just keeping it as one channel to one channel, it's going to output it into 10 channels. So really what that means is that this layer has like 10 different sets of weights that it's using to create 10 different outputs. So we're sort of expanding our space of data at this stage of the neural network. And again, we're going to do 3x3 weights. And this really simple 2x2 pooling. Then this next layer is going to take in these 10 channels sort of the output of that first convolution and use a 5x5 window. So we're looking at sort of larger spatial context now, and then outputting even 20 channels. So we're sort of expanding even more. So this is going to have 20 different sort of convolutions that it's applying to these 10 channel inputs, etc. And again, we're going to pool to reduce our feature space even more. And finally, we're going to have this last layer, last convolutional layer, which is going to take in those sort of 20 channel inputs, and it's going to look at a 15x15 window, so looking over a much larger spatial context, and then outputting it sort of 50 times into this 50 channel image. And so now we have 50, our sort of output will be 50 different images or a 50 channel image, but it's going to be much, much lower resolution because we've done this max pooling a bunch of times. We've sort of started integrating over larger spaces, which means you kind of lose the edges to a certain extent. And then what we're going to do is start passing this through linear features. And so you end up doing this because often what you want out of these neural networks isn't like an output image. You want like a number or a class or something like that. So the way we do that is then with linear transformations again. So we have this linear feature, which is 4,200 inputs and then 800 outputs. So it's just, you can think of like a linear transformation that's taking in a vector that's 4,200 long and then outputting a vector that's 800 long, and 800 to 100 and 100 to 10. And so the reason that we're outputting 10 is because this is a network for classification. And the way that you typically implement this is by having sort of an output vector, which is your number of classes, which you sort of interpret as the probability that your input is in each of this class. So the maximum probability is what it's most confident that it's going to be. It's typically how you train these things. And then again, forwarding through it. So we take our input, we pass it through our first convolution, our first relinearization, our first max pool. We do that again for the second convolution, this third convolution. And now we need to get it into our linear layer. So to do that, we actually need to flatten it. And so for this input, once you sort of pass it through all these things, you're going to have 4,200 pixels, basically. So when you flatten it, it becomes a 4,200 length vector. This length is going to be specific to the set of convolutions you have, the sizes of them, and also the size of your inputs. There is also, PyTorch has like what they call a lazy linear layer, which will sort of automatically infer that for you. But if you don't use that, you need to do a little math to figure out what the size of your input will be once it gets through here. So once we flattened it, now we're just going to go through these linear layers. So do our linear layer, relinearize again, linear layer, relinearize again, just have those activation functions. Then it'll finally return this x, which is going to be, again, just a vector with 10 slots, one for each class, functionally. So you'll see this a lot for image classification. Even a simple network like this is really powerful. And you may be saying, well, what's the point of using these convolutions to get the sort of spatial information if we just flatten it? The sort of idea is that like by this point, you're no longer creating spatial maps. It's like much more uninterpretable than that, much more in some sort of weird feature space. So by flattening it, you're not, the spatial information has already been collected into each of those pixels of your output image. So you can also use a network that spits out one number if you're going to be trying to infer a specific value. And this is really just going to be the same as what we had above, but instead of just doing a 10 output vector, you have a 1 output vector. So it's just going to be that one output. But other than that, this architecture is exactly the same. We've just gone from 100 to 1 instead of 100 to 10. So again, a really simple neural network, but it can actually be pretty powerful. So just to talk briefly about my own work. So I've been training a neural network to see if it can invert numerical models. And so what I found is that this network architecture can infer sort of the ratio of this advection to diffusion in these landscapes with a really, really high degree of accuracy. You can see here, it's just that output. So it does really, really well. Some drop off over here. But even a really relatively simple and small neural network here can be very, very powerful. And you also don't have to do everything in series either. You can do layers in parallel, sort of any way that you want. So here, again, this is a really similar neural network. We have these 3 convolutional blocks, but here they're all 1 to 10, and they have different sizes. So 3 by 3, 5 by 5, 15 by 15. And then one more convolution that takes in a 30 channel image, does a 7 by 7 convolution. And then finally, these linear layers. So I said here, like this number is wrong because in this case now the size of this output is going to be different than what I had before. So I'd have to either use a lazy linear layer or do the math myself to figure out how many output pixels are going to be after this last convolution. But so here, when we do our forwarding, we're going to do it slightly differently. So all these 3 convolutions, conv1, conv2, and conv3, take in the same input, but we're keeping track of their outputs separately. So x1 is what goes through the first convolutional unit, x2 is what goes through the second convolutional unit, and x3 is what goes through the third convolutional unit. Then we're just sort of going to concatenate these all together, so it becomes, in effect, a 30-band raster. So again, each of these convolutions is outputting 10 channels or bands, whereas 10 neurons, however you want to think of it. So we add them all together, and we feed that through our last convolution, and then flatten and do all those linear layers. And so in this way, instead of like in this architecture, we're sort of looking at larger and larger spatial contexts over time, or as things move through the network. Here, we're looking at all 3 spatial contexts at once, separately, and then sort of feeding it together and aggregating it all. So I've done this to try to figure out, the relative importance of different spatial scales, maybe. So you can have these 3 different spatial scales happening simultaneously, and then maybe turn one off and see how the network performance changes. So far, I haven't gotten any interesting results. I don't have anything interesting to share with you for that. So let's go back to our really simple neural network, which did an okay but not great job after 5 epochs. Now we've trained it for 50 epochs, and we'll see how it did. You can see, again, hit that really slow, low value overall, but then maybe started decreasing more and more. So not a huge reduction in loss, but you can see these weight values have like really found their trajectory and now are slowly approaching what's going to be 1, -1, and 0, which makes sense because in our example convolution, that's what all these weights actually are. So it's by letting it run longer, we've actually started to find our way into something maybe that's a little more realistic for this convolution. Again, when we look at it, this looks much closer to our example output. And then looking at these weights, you can see it's still actually pretty far off. So this should be like a -1, 1, -1, but we're like getting there. But it's done a pretty good job of capturing this this input. These are really similar, at least visually. You can see the loss is really, really low. Um, so presumably, given the fact that it looks like these weights are still maybe approaching a value, let this run much longer, maybe it would find its actual these actual values. But so you're going to need to play around with how many epochs you would need to train things on. Um, and, if you recall what these graphs looked like, I should have saved them from training after just 5 epochs. Like it looked like it had done maybe as good a job as it was going to do. It had oscillated around and then found what seemed like a good enough value. But actually, by letting it run much longer, it's performed very well. Okay, so I've gone over some different architectures of neural networks. I also want to talk a little bit more about like actually meaningful data loaders, and what you can do with them, and why you'd want to use data sets. Sorry, I should say data sets, not data loaders. So here's a data set that I used for training the network for this. So I had all my data sort of stored in a SQLite database, all the information about my model runs, and then my model run directory somewhere else. So I had to create a custom data set to deal with this. So here, this data set takes in a database, a directory where all my different landscape files were, and then a query to pull out that label. So again, we sort of set all this as variables in this data set object that I've created. And then each time you want to get an item, it says, okay, I'm going to pull out. So when I set it up, I've got a list of runs from this database. And I'm going to pull the run name from that list for the specific index that's been passed. I'm going to pull out that data file from that specific directory for that specific run name. I'm going to pull the label or the thing I'm trying to predict from that database as well, just with this query. And I'm going to load this array and change it into a tensor for PyTorch. You can see here I've cropped out the edges to deal with some edge effects, etc. But then this data set returns this data array, this label, and in this case also the run name. That was for some debugging. So now I can just pass this data set into a data loader, and then PyTorch will sort of batch it for me in the way that the neural network expects. And I sort of neatly tucked away all the data processing and stuff I need to do here. So that's one data loader, data set. Here's a different one. So here, this is for getting Landsat data off Google Earth Engine and then pairing it with a different data set. So you have some Google Earth Engine specific things like bounds, the specific collection, the length, so the number of what do you call it? Like image samples I want from this, the size of it, the scale, the bands, etc. We're just sort of setting this all, and then also this label function. And then I have this get image array function, which, for given a specific point, it does all the sort of necessary Landsat processing, and then returns it. And then I have my get item function, which for a specific index, which really corresponds to a point, it returns the image sort of centered on that point, and then the value from whatever this label function is that I've passed. And then again, this set of points is actually, it's just a set of random latitude and longitudes. So this is really going to do is it's going to create 1,000 random points, maybe in a set of bounds that you've given it. And then it will pull that image for that random point off Google Earth Engine, and then pull the value from whatever your label function is. So sort of by building this data set, I've now created something that I can path to PyTorch, and it'll handle, grabbing the data from the wire, offline for me, basically doing random sampling if I across my specific region of interest, because I don't have enough time to train across everything, and I want it to be just a random sampling, things like that. So these are the type of things you can do by building these custom data sets. That's where you sort of handle some of the data collection, aggregation, and processing stuff before passing it through your neural network. And so running towards the end of the time. So lastly, I just vaguely wanted to mention Torch Geo. This is something I haven't really had a chance to play with in much depth, but it's an infrastructure for Microsoft for working with spatial data, primarily satellite-based data sets. So it basically provides data sets, um, you know, for Landsat, for other satellites, for other spatial data sets that are out there for you, and then stuff to help, uh, with like sampling it randomly, things like that. So it does some of the stuff that I did here for you, just by default, but for a lot of it, you need to have the data itself. So can't miss some stuff it'll grab for you, some stuff it won't grab for you. Um, Personally, I've really struggled with getting some of it to work, but it's out there and it's something to um, look at if you want to work with satellite imagery specifically. Um, so I think that's basically the end of our time. Got some time for questions if anyone has any. I know I threw a lot at you.
Great. Thanks so much, Joe. Go ahead and you can either just jump in with a question. I think it's a small enough group, or post something in the chat.
Yeah, Mark.
Hello. I'm wondering, so this seemed to go over like a two-dimensional convolutional neural network pretty thoroughly. So that was very cool. Thank you. Um, I'm just curious if you have any comments on like working with three-dimensional convolutional layers, and any sort of maybe differences or challenges those pose as opposed to the two-dimensional ones.
I can't really speak to that. I haven't worked with it at all. Um, I imagine in a lot of ways it would be similar from like a neural network architecture standpoint. Um, just you can imagine like a one-dimensional convolution neural network where it's sliding, this set of 1D weights sort of over this line. So all I can do, since I've never used them, is sort of expand that intuition again from 1 to 2 to 2 to 3. But I have no comments besides that. Sorry.
Sure, gotcha. Okay. And then I guess maybe a next question. This is kind of more torch specific, I guess, since I'm a little more familiar with Keras. The if you were going to add like an LSTM or like a recurrent layer, like do you generally put that into like just a single class, where you're doing because I guess you have the forward like method, right? So you would just put those layers in with the rest of the conv layers also, or do you actually like separate them out into distinct ones?
Yeah, it becomes like a little more complex, but you in your initialization function, you
Mhm.
create one of these RNNs, and then you place it in as part of your forward method, as needed for your architecture.
Got it. Okay. Thank you.
No problem. Yeah, and I haven't used Keras or anything else, so I can't compare, unfortunately.
Fair. Yeah, it's all the same under the hood, more or less.
Yes, and someone asked about the Prince book, so that's Understanding Deep Learning by Martin Prince. Um, yeah, you can get the full PDF here at this link. Yeah, I've really enjoyed it.
Okay, other questions for Joe? If not, let's give him a digital round of applause. And thanks again. This has been great. The recording will be posted on the CSTMS YouTube channels. So if any of your friends or colleagues want to check it out, we'll be sending out an email as soon as it's up.
Yeah, and just again, this notebook is on my GitHub. It sort of has all the code that I slowly pasted over, and then some more commentary like that kind of goes over the stuff that I was saying as well. So it's there for you if you need it.
Awesome. Thanks.
Thanks everyone. Thanks for coming.